Hello and welcome to another session of symmetry and group theory in chemistry. We are now talking about direct product of representations. We have so far learned about reducible and irreducible representations and character tables. We have seen that the character table is a collection of characters of different irreducible representations, and now we are going to see how the products respond to various conditions. Again, I'm your instructor, Saurabh Bhaktibodh, in this presentation. The key idea is the characters of the representation of direct products are equal to the products of the characters of the representations based on the individual sets of functions. So if you have character of one R, one related to symmetry operation R and character of two related symmetry operation R, then their product is equal to the character of R. So that means we can multiply 1:1 characters and we can conclude and infer many things out of it, and particularly this finds its applications in quantum mechanics and in general talking about vanishing or non-zero integrals. That is very helpful in predicting this kind of quantum mechanical treatment. For example, to begin with, we will take a character table for point group C4V. C4V has a typical set of elements E, C2, 2C4, vertical planes, two diagonal planes, and the irreducible components of that particular point group is, as you can see, A1, A2, B1, B2, and E. We know that A1 and B1 and A2 and B2, they are one-dimensional irreducible representations, while E is a two-dimensional irreducible representation. Now, what happens when we multiply the characters? For instance, if I multiply A1 with A2, so with multiplying A1 with A2, what I have is 1 into 1 is 1, 1 into 1 is 1, 1 into 1 is 1, minus 1 into 1 is minus 1, and minus 1 into 1 is minus 1. So this is the result of A1, A2. If you multiply B1 with E, so this is B1 and this is E, the result comes out to be, so 2 into 1 is 2, minus 2 into 1 is minus 2. The rest of the elements are obviously zeros because there are 3 zeros here. If you go for A1, EB, taking 3 simultaneously, now you have E2, you have A1, this is A1, then you have E, and then you have B2. So if you multiply all of these, so you have 2, 1 and 1, that becomes 2. If you have minus 2 and then 1 and 1, that is minus 2. And because E contains 3 zeros, and the rest of the product would be obviously zeros. If we talk about the square of E, 2 square is 4, then minus 2 square is 4, zeros would have a zero value. So we have a collection of various products of representations, and now it's quite easy to make some inferences out of it. How come? Let's proceed. Here we see that A1 into A2 and A1 into A2 is just characters of A2 1, 1, 1, minus 1, minus 1. So we see 1, 1, 1 and minus 1. So A1 into A2 is equal to A2, that we can simply observe by looking at the character table. If we talk about E square, so E square, that is equal to 4400. A simple logic tells us that if you add the 1 plus 1 plus 1 plus 1, that becomes 4, except E. This are all 4, this is 4. And then if you have this, you talk about this, so you have minus 1, 2 minus 1 and 2 plus 1, result is going to be 0. Here again 2 plus 1 and 2 minus 1, result is 0. 2 plus 1 and 2 minus 1, result is 0. So E square is equal to summation of A1, A2, B1 and B2. That can be easily also observed or calculated using standard reduction formula that we have seen earlier. Similarly, if you find for B1 with E, so B1 and E product gives 2 minus 2. These are the characters of E itself. So here we are getting E. If you have three things, 2 minus 2 000, 2 minus 2 000, so that is E. So A1 into E into B2 comes out to be equal to E. A1 is one dimensional, E is two dimensional, B2 is one dimensional. So if you multiply 1 into 2 into 1, it is again 2 only. So this way, it is quite easy to make some inferences, some conclusions out of these products of representation. And what are they? For example, if we have a product of one dimension with one dimension A, basic, you get A. You multiply A with B, you get a B. That's an antisymmetric one-dimensional irreducible representation. If you have A into E, 1 into 2, that is equal to E, that is two-dimensional representation. B into E, 1 into 2 is again E, that's a two-dimensional representation. 1 into 3, A is one-dimensional, T is three-dimensional, so 1 into 3 is 3. So the product is three-dimensional always. A one-dimensional B into T would always give a three-dimensional. So B is one-dimensional, T is 3, so you have three-dimensional product. A into E1, that is 2. E1 is two-dimensional, A is one-dimensional, result is E1. So is the case with E2. And so is the case with B for E1 and E2 respectively. So the dimensions 1 with 2 would always result a two-dimensional representations in their answer. So when we are doing it, actually we are not bothering about how to decompose a reducible set into an irreducible components. The product would always be the same. There are certain observations also. So if we multiply by a term G with G, so Gerard with Gerard or Gerard with Gerard, we get G. You have U with U, unGerard multiplied with by unGerard gives G. U and G gives U. And similarly, if we talk about the primes, so a single prime multiplied by prime gives a single prime. A double prime product with double prime gives a single prime. A single with the double prime product gives a double prime. Sometimes you have some subscripts like A1, A2, 1, B1, B2, etc. We have generally observed that one subscript with 1 gives 1, 2 with 2, and 1 with 2 gives 2. So 2 into 2, that is if A2 and A2 kind of thing, the result would be A1 itself. If you have A1 with A2, the product would be A2 and so on. So these are some generalized products that are really very helpful in calculating various things that will be useful for quantum mechanical calculations. If you talk about the twofold degeneracy, then if you have 2 into 2, there's 2 into 2 is 4. So four-dimensional representation would be summation of A1, A2 and E. So you have A1 plus A2 plus E2. So A1 is one-dimensional, A2 is again one-dimensional, E2 is two-dimensional. So 2 plus 1, that is 4. So E1 into E1 is equal to A1, A2 plus E2 that you can observe. Similarly, when you have E2 with E2, the result is same A1, A2, E1. So E2 square is the same thing. Similarly, E1 with E2, now this has a point of difference. Here E1 and here 1 E2. The product is B1 plus B2 for E1 for a certain character table that you will observe later. E into E in general is equal to A1 plus A2 plus E. So one-dimensional plus two-dimensional irreducible representation. Had it been a three-dimensional thing, so 2 into 3, that is 6. E is two-dimensional, T is three-dimensional, the product is 6. So the product is actually T plus T, T1 plus T2. This is three-dimensional, this is three-dimensional, the total is 6. Your answer is verified. Similarly, E with T2 gives T1 plus T2. A six-dimensional, two-dimensional into three-dimensional results comes out to be 3 plus 3, T1 plus T2. And T1 into T1, that is 3 into 3, that is 9. And that would be offering you A1, 1 plus 2 plus 3 plus 3. So 3 plus 3 is 6, 6 plus 2 is 8, and 8 plus 1 is 9. So T1 into 1 is equivalent to A1 plus E plus T1 plus T2. So this is some generalized form that you will receive in coming text and coming various applications of group theory. If you multiply T2 with T2 for certain applications, you will find that it's again a 3 into 3, that is A1 plus E plus T1 and T2, the product would remain same. T1 into D2 is give, instead of A1, you find A2 and A2 plus E plus T1 into T2. So this kind of generalizations are indeed very helpful. If you talk about the point group of linear molecules, summation terms, so sigma plus into sigma plus gives sigma plus. Similarly, sigma plus and sigma minus is antisymmetric, that gives sigma minus. Sigma into delta is delta itself. Delta into delta is sigma, sigma plus tau. Here they are using different conditions. For one-dimensional is sigma, and for two-dimensional it's delta, and so on. So these relations, although they are not very common, but may be useful for infinite groups or linear groups like C infinity H and D infinity H. There is a warning, there is a caveat. Groups where the subscripts 1, 2 and 3, for example D2, here 1 into 2 is the 3, 2 into 3 becomes 1 and 1 into 3 equal to 2 that we have seen in earlier. It is a different case, so please be cautious about this change. And for pointers where the principal axis is C2 or C4, E into E becomes A1 plus A2 plus B1 plus B2. That is a slightly different thing. So 2 into 2 dimensional is A1 plus A2. You have A1, that's 1 plus 1 plus 1 plus 1. That comes out to be 4. So that has to be taken due care. That's all for this video. You will be finding the applications of this video in various parts of group theory, and that will be very helpful for reducing the pain that is involved in mathematical calculation. Thanks for watching. You have been very great audience. Thanks again, audience.